Hello guys, I'm here for another problem and example. In this session I want to talk about some heat exchangers. But first, as always, let me introduce reference, which is heat transfer book from Professor J.P. Holman. You can have this book and work on this book from 10th edition. Okay, the chapter 10 of this book actually talks about heat exchangers. You can go to page 536. Okay. Okay, I wanna work on these examples. Design of shell and tube heat exchangers. It is a practical, somewhat practical example to design a heat exchanger, shell and tube kind. So let us do it and design these heat exchangers together. Water at rate of 30,000 lbm per hour, or 3.783 kilogram per second, is heated from 37.78 to 54.44 degrees Celsius in a shell tube heat exchanger. Okay, on the shell side, one pass is used with water as the heating fluid. Okay, and the mass flow rate of that would be 1.892 kilogram per second. Okay, so this fluid entering the exchanger at 93.33 degrees Celsius. So we have the temperature of entrance of that, but we don't have any output temperature of second fluid. Both of fluid in this exchanger are water. The overall heat transfer coefficient is 1419 watt per meter square degrees Celsius, and average water velocity from 3/4 inch it equals 1.9 centimeters in diameter. Okay, so the velocity is 0.366 meter per second, and we have some limitation in space, and the tube length must not be longer than 8 foot, which is 2.5 meters. We should calculate the number of tube passes and the number of tubes per pass, and the length of the tube consistent with this restriction. Okay, first of all, okay, let's get started. And sorry. Okay, let's get started and solve these examples together. Okay, first I have to draw the diagram of these kind of tube and shell. Okay, so as we talked before, This would be cross section 1, this would be 2. Heating fluid and cold fluid, cold stream and heat stream. Okay, this is TH, T and A axis, capital TH 1, TH 2, here TC1, and here TC2. This is 60 degrees Celsius. Sorry, we don't have, we should calculate it, then I don't write it. 93.33 degrees Celsius. This is 37.78 degrees Celsius. And this is 54.44. Okay? First we should calculate this temperature because we don't have it. Then let's do it. Okay. We know that Q equals m dot C, heat capacity of cold stream, and delta T C, and equals m dot hot C, heat capacity of hot, delta T of hot. Then we have this one, this one, this one. We have all of them, but we don't have this one because we don't have this temperature. We should calculate this one. Delta TH equals 3.783 kilogram per second for m dot C, multiplied by 4182, which is heat capacity of water in cold temperature, and delta C will be difference between two temperature, 54.44 minus 37.78, okay, divided by what? M dot H, which is 1.892. Here you can see these parameters exactly in this example, okay, and again 4182 for heat capacity, because we can assume these two are different, okay. Then delta TH will be 33.33 degrees Celsius, and we have this temperature because delta TH equals TH1 minus TH2. Then TH1 would be TH2 minus TH1. TH1 would be 60 degrees Celsius, okay. So I can write it here, 60 degrees Celsius. Okay, let me continue. Okay. And now we can we can calculate Q from the formula MC CC, one of them, this one or this one. delta TC. Then Q equals 30.700 for 4182 multiplied by these numbers. Okay, the value will be exactly 263.60 kilowatts. Okay, so let me erase this section. Okay, our Q is defined here. Q equals 263.6 kilowatts. Okay, you don't need it anymore because I evaluate that Q. But the other parameter I need is delta Tm. Delta Tm. Why? Because I need to evaluate Q equals U overall transfer A Q U A delta Tm. I don't have it, and I want this one, so I don't have it, but just have this one and this one. So it should found the value of this parameter. I should evaluate that. Okay, it had a formula. You can see in equation 1012. Okay, TH2 minus T capital TC2 minus TH1 TC1 ln of TH2 minus TC2 divided by, sorry, I need a parenthesis here, TH1 minus TC1. Okay, if I put the value here, 93.33 minus 54.44 minus 60 and 37.78 ln of, again, 93.33 54.44 divided by 60 minus 37.78. Then delta Tm equals 29.78 degrees Celsius. Okay, let me write it exactly here because I need it in following. Okay, degrees Celsius. Okay, and I don't need it anymore. Let me erase that one. Okay. Okay, very excellent. Okay, next step. What is the next step? To use A1. A1, this one. I should use this one. What is the formula of that? A equals, okay, A equals, let me name that A1. Okay, heat transfer area, overall heat transfer area. Okay, A1 overall heat transfer area. It is different from A2. I will explain it and name it in following. Okay, then A1 from this formula equals 263. I was talking about finding A1. How can I find A1 from this formula? Okay, but I first I should find delta Tm. Okay, I cannot complete this formula because I don't have delta T. Oh yeah, I found it here. Sorry, I made a mistake. I have delta Tm, so this is Q divided by U. What is the evaluated U? U was 14.19. You can see
and the example 14 and 19. Okay, so here 14, 19, delta Tm is 2978 degrees Celsius. Because this is kilowatt, I should multiply it to 1000. The answer would be 6.238 meters square. Okay, then I should write it here. Overall heat transfer area 6.238 meters square. I don't need these formula anymore. Okay, let us erase that one. Okay, then what do you need? Anything? Okay, I have the formula for calculate the area of cold section. What is that formula? This one. M dot mass rate, mass flow rate, density, velocity, and A2. What is A2? The cross section of tubes. Okay, cross section of tubes. M dot cold, this one has a cross section. Then this cross section, whole cross section. Okay, better say whole cross section for all the tubes is that one. Okay, so I need to know that one. A2 equals m dot c divided by rho and u. This is velocity that we have it. Sorry, this is capital U and this is a small u, which is velocity. This u is velocity. Velocity of cold fluid. Okay, then the value of that is 366 ml per second. Okay, let me calculate this one. A2 would be 3.783. We have it, and rho is 1000 kilogram per meter cubic for water, cold water, and velocity meter per second for velocity. Okay, the answer for A2 will be 0.01034 meter per square. Okay, then A2 will be like that. Need a 0 here. 1 C34 meter square. Okay, then okay, just let me use the place of that. Okay, but we should calculate PD. Okay, but first I need to know N. N is number of tubes per pass. Okay, I can use it from here. If I divided A2 by PD square divided by 4, what is D? D is diameter of tube, which is 3/4 inch. We have it. Okay. Okay. So the value of that is 1905 meter. Okay, in meter, or 3/4 inch. Okay, I can use it to calculate n. Then I can write here 0, 1, 10, 34, which is a 2, multiplied by 4, and P, this diameter square, the n would be 36.3 or 36. Then n would be 36. We should try it if our restriction would be okay. Let me erase these one because I don't need them. Okay, next I need to calculate PD. P and D here. 1905 would be 0598. Okay? Then my PD equals 0.0598 meter. Okay, that's it. What do you need more? I should calculate the length of pass. Okay, so what I have to do now is to write a formula. N PDL. L is length. L, length of tube in each pass is L. P is perimeter and N number of tubes. Okay? Then it would be equals to A1. Am I right? It will be equals to overall heat transfer coefficient, heat transfer area. Then I have this one, I don't have this one, I have this one, and I can here actually calculate that one. 6 to 38 divided by 36 multiplied by 59. Sorry, this is 8. 59, 8, which was PD. Okay, it would be 2.898. But as we have a restriction here, 2.438 is actually 438 meter is restriction, but this value, this L, is greater than 1. Then we cannot accept that. So what we should do now? All of this calculation was for when in situation we have one pass. Okay, one pass. But we have to calculate for two pass because this L is greater than our restriction and limitation. Then what we should now? I will say. Okay. Now. Okay. Now we want to imagine two passes. Okay. We should actually set a formula for that one. A, we named it total. This is A1. but this is A1 will change. This is for one pass. This is for one pass. And this is for no, it is not different. Then I should change the overall heat transfer area for two pass condition. Okay, but Q is the same at any condition. Okay, A total U F delta Tm. F is a factor. We should calculate that. Okay, we should calculate F first of all because we have delta Tm. We don't have F. We have U, but we don't have this one, but we have it. We should calculate it A from this formula, but we don't have it. We can go to figure 10.8. This figure. Okay, we have this figure. We should calculate P and R in here. R and P. Let me calculate it. P equals T2 minus T1, capital T1 minus small t1, and R equals T1 minus T2, small t2 minus small t1, and I will show it in this picture to you. Okay, this is small t2. As you can see in this picture, we should name them. This temperature is small t1. This would be capital T2, and this is capital T1, and we should put it in this formula. Okay, if you do that, 60 minus 93.33 divided by 37.78 minus 93.33, it would be, P would be 0.6, and for R, capital R, 37.78 minus 54.44, 60 minus 93.33, R will be, okay, this one. Okay, if I choose P here from this diagram, and R 0.5 from this diagram, it will be someplace over here. Someplace over here, okay? Here, maybe here. Our F would be 0.88, okay? 0.88. I need this F, okay, here. I will write it 0.88. I should multiply by delta Tm. I don't need this something anymore. Let me actually now I have F, okay, and now I can calculate a total, which would be Q divided by U F delta Tm. If I put the value that 276.6 divided by, oh sorry, this one 19, F is 88, that one, and delta Tm is 2978, that one. A will be will be 7089. A total for 2 pass. It is for two pass. 7089 meter. Okay. And I should now calculate. I have a formula here. I should now calculate L. We have 2 passes. Multiply by n, multiply by perimeter, and multiply by the length of each pass. Okay. Then L will be 7089, which is a total, divided by 2. 36 is n, and PD is where is that? 59, 8 meter. L will equal to 1.646 meters. We can see that this L is smaller than that. So our answer will be N36. Okay, the answer of these examples. Number of passes is 2, and length of the tube per pass is 1646 meters. Okay, these 3 was the answer of these examples. Thank you for watching. Have a nice time and take care. Bye bye.